We're going to finish up chapter 2 today, and we have two more sections, sections 4 and 5. Now, in section 4, we deal with something called symmetry. Symmetry is simply a mirror image. We have three types. The first one is about symmetry about the x-axis. Now, that's vertical, up and down. The next one is symmetry about the y-axis. That's a horizontal transformation or symmetric. And then the third one is about the origin. So that's like, for example, from the first to the third quadrant or from the second to the fourth quadrant. Now, to be symmetric about the x-axis, so if we had a point at 1, 2, to be symmetric about the x-axis, it would have to have a point at 1, -2. So to be symmetric about the x-axis, the y value changes signs. So the y value changes from positive to negative or negative to positive. To be symmetric about the y-axis, we have a point here at 2, 1. To be symmetric about the y-axis, it has to go to -2, 1. So the x values change signs. So it goes from +2 to -2 and vice versa. The x values change. To be symmetric about the origin, both x and y values change signs. So if we had a point here at 2, 3 in this quadrant, the first quadrant, then about the origin, it would go to -2, negative. So notice the numbers stay the same. Only thing changes is the sign. Right? So for example, also, we know some functions already, like the quadratic equation. We know that one is already symmetric about the y-axis. Because the point 2, 4 has a mirror image at -2, 4. Notice the x values change, so it's across the y-axis. And we also know some functions already that are symmetric about the origin. This is the cube root of x. So 8, 2 has a mirror image at -8, -2. There's that point is symmetric about the origin. So the point 8, comma 2, negative 8, comma negative 2. So that's symmetric about the origin. Example of a function that's symmetric about the x-axis. This is when y changes signs. Let's just say, let's try that. Well, we could put it this way. If we drew this one, x squared is like this, but now with this negative in front of there, what that means, it's now all my y values are negative. So that would mean something like this. Because the x squared is up here, but when the negative's out in front, it shifts. So now it's symmetric. It's flipped. This point here matches this point down there. The problem with being symmetric about the x-axis is if it's symmetric about the x-axis, it's not a function anymore. In other words, if we had 2, 4 here, symmetric about the x-axis will make it negative 4. And it's not a function because it fails the vertical line test. So those are the problems we have when we have that kind of transformation. Now, there's an algebra test that we use to see if it's symmetric about the x-axis, the y-axis, or the origin, but I'm going to show you a shortcut instead of doing that. We're going to talk about even versus odd functions. If a function is even, then it is symmetric about the y-axis. And I'll show you what that means. If a function is odd, then it is symmetric about the origin. So how do we tell if it's odd or even? Look at the exponents of the variables. There are certain situations we have here. One, if all exponents are even, the function is even, therefore it is symmetric about the y-axis. For example, let's see what that looks like. All the exponents are even. So this is an even function. So that's the first condition. Number two, if the function is a constant, then the function is even, and symmetric about the y-axis. Okay, so the first one is pretty easy. If all the powers are even, we know that from this equation, x squared. If the only power you have is even, then it looks like this. So it's symmetric about the y-axis. But let's look at a constant function. Let's say the constant function was 3. It's a horizontal line. Because it's a horizontal line, any x value I pick, it's going to have a mirror image on the other side. So a constant, by definition, is symmetric about the y-axis because it's horizontal. So the first one, if all the powers are even, it's even. It means symmetric about the y-axis. If the function is a constant, in other words, y equals 3, if there's no x values, then it's an even function, therefore symmetric about the y-axis. We can combine those two. If a function if a function has both even exponents and a constant, then it is an even function and symmetric about the y-axis. So we see this example, since all the x powers are even, and we have a constant, this is an even function. So evens can only, the constant numbers can only belong to even functions. So that means the only way you can have an odd function, if a function has only odd exponents, then it is an odd function, and therefore symmetric about the origin. In other words, if you have odd exponents and a constant, it's neither because you can't mix and match. Here's an example. If there's no exponent, it automatically means there's a 1, which is odd. So this is an odd function, which means it's symmetric about the about the origin. Any other combinations means that the function is neither even or odd. For example, if we had that's neither because one's odd, one's even. Neither because you have an odd exponent, which is 1, and you have a constant. So let's look at an example. This is example. Tell me if this is odd, even, or neither. 5x to the 7 minus 6x cubed minus 2x. The only variable, we have 3 variables. It's a 7, odd, 3, which is odd, and a 1, which is odd. So this is an odd function. So therefore it's symmetric about the origin. Five x to the 6, 3x squared minus 7. This is even, and a constant, which is even. So this is an even function, which means it's symmetric about the y-axis. Now, mathematically, to test symmetry, one, to test symmetry about the x-axis, to do that, change y to negative y and see if you get the same equation. So if we had y equals 3x minus 3x squared minus 2x plus 1. What we have to do, change y to negative y. Because this is here, we could move it to the other side. So change all of these signs. So that becomes positive. This becomes a negative 3x squared. This becomes a positive 2x. That becomes a negative 1. So are these two equal equations? No, because all the signs are opposites. So not about the x-axis. There really isn't one about, the only way you could have one that's symmetrical at the x-axis is if we had y squared equals x. Because what would happen there is for us to solve for y, if we square root both sides, we have to put a plus or minus in front of the x. So that means there's one y value for two x values. This equation would look like this. So for whatever x you give me, I have a positive and a negative y. And it doesn't matter because the squares take care of it. So that's how you do it mathematically, right? So that's the end of that section of symmetry. Any questions?